Hello friends, welcome to this video on one-sided Chebyshev's inequality. In this video, we will see about the statement of one-sided Chebyshev and then we will see how to apply them to find the bounds of any given problem. Come on, let's get started. For a statement of one-sided Chebyshev inequality, we see that if x is a random variable with mean 0 and finite variance sigma square, then for any positive value c, probability of x greater than or equal to c will be less than or equal to sigma square by sigma square plus c square. The major difference between Chebyshev and one-sided Chebyshev is that when we have a Chebyshev, we have probability of modulus of x minus mu to be greater than or equal to c. So whenever there is a modulus, we will be able to find an upper bound as well as that of an lower bound. But when it comes to one-sided Chebyshev, we just have greater than or a lesser than alone to be estimated for. The main point to be noted over here in this formula is that this works only when mean is going to be 0. So in your original Chebyshev formula, the value called as mu will become equal to 0, leading you to x greater than or equal to c to be less than or equal to sigma square by sigma square plus c square. So this is your statement of your one-sided Chebyshev, and there can be corollary or the outcomes of it which will be useful for us to apply them to problem. The corollary states that if x is a random variable with mean mu, notice that it is not 0, now it is becoming non-zero, which can be stated as mu, and it has a finite variance sigma square, then for any c greater than 0, your x greater than or equal to mu plus c will be less than or equal to sigma square by sigma square plus c square, and x less than or equal to mu minus c can be less than or equal to sigma square by sigma square plus c square. So this modulus of x minus mu, we are able to split over here as 1 to the positive side and 1 to the negative side, and we know that for sure this is going to be less than or equal to a quantity. So this becomes fixed, rather this becomes the upper end and this becomes your lower end for the value. So we will start applying one-sided Chebyshev's inequality to solve problems. Come on. Problem number 1. The number of items produced in a factory during a week is a random variable with mean given as 100 and variance as 400. Use one-sided Chebyshev's inequality to find an upper bound on the probability that this week's production will be at least 120. So we have been asked to use one-sided Chebyshev and we are being provided with a mean which is going to be 100. Mean 100 is going to be a non-zero quantity. So I cannot be applying the general statement with mean 0, but rather I will have to apply the corollary with mean which is non-zero. So I will have to choose for one of these formulas depending on the bounds they have asked me for. So they have asked me that the week's production is going to be at least, so x has to be greater than or equal to 120. So where our x greater than or equal to 120 happens? Over here. So we will try applying this formula of Chebyshev one-sided inequality to get our solution. So copy paste the formula over here. So we have that probability of x greater than or equal to mu plus c is less than or equal to sigma square divided by sigma square plus c square. The quantities which we have in hand are, we have been given mu is equal to 100, variance which is sigma square is going to be 400. The second common mistake which usually we people do is, the first one being when mean is given as 100, we usually go to apply the first formula, but that is applicable only when mean is 0. The second thing is that we'll have to be cautious about what is given, whether this is going to be variance or standard deviation. If it is standard deviation, then you will have to square the data and then use it. If it is variance, you can directly use it. So this has to be less than or equal to, by the formula sigma square divided by sigma square plus c square. The next objective is to find the value for my c. because I know that sigma square is going to be 400 divided by 400 plus. So this C, if you take it as 120, then the problem will topple. The C is not 120, but rather mu plus C has been given as 120. Mu is already 100, so C will be equal to your 120 minus 100, that makes it as 20. So if C is 20, your C square is again equal to 400. So that makes the probability as half. So keep in mind, when mean has been given to you, you must not apply the first formula which has been given, because this is applicable only when mean is 0. So you cannot use your C directly. You will have to estimate your C from the given data mu plus C. So mu is given, so subtract it from it and then apply your formula. Now, the second part of the question is they are asking us to compare this with the upper bound using Markov inequality. So, what we know about Markov inequality? By Markov inequality, we know that probability of x, which is greater than or equal to a, has to be less than or equal to e of x divided by a. So I want probability of x to be greater than or equal to 120 for my problem. So if it is going to be greater than or equal to 120, this will less than or equal to e of x. E of x represents the mean, mu of the data. What has been given as mu for me? It has been given as 100. So this will become 100 divided by 120, in which case this will be equal to 5 divided by 6. So we say that the value for Markov inequality, the bound is going to be less than or equal to 5 by 6, but which when it comes to your one-sided Chebyshev, this is less than or equal to 1 by 2. So which you would think is going to be more stronger? Your one-sided Chebyshev is going to be more stronger because this is less than or equal to 0.5 and this value is going to be more than that of the 0.5. So you can say that one-sided Chebyshev provides more closer solutions or more appropriate solution or more closer bound than the Markov inequality. Okay. So in this way, we have compared both of them. Markov inequality we have learned in the last class and as well as one-sided Chebyshev. Okay. We'll move on to the next problem. Let x follow exponential distribution with parameter 1. Using Markov inequality, find an upper bound for probability of x greater than 3. Compare the upper bound for probability of x greater than 3 obtained through Chebyshev's inequality. Also estimate the actual value of x greater than or equal to 3. So the problem has 3 parts for me over here. So the first part using Markov inequality we will do. The second part using one-sided Chebyshev's we will do. And the third part using your actuals we will do. By Markov, what do we know? We know that probability of x greater than or equal to a as less than or equal to e of x divided by a. So now my x follows exponential with parameter as 1. So my lambda is going to be equal to 1. So if lambda is 1, what do you say about the mean of the random variable? Mean of your exponential distribution is 1 by lambda. So that will again remain to be equal to 1. So this will give me e of x as 1. For a, I will have to replace it with the question, which is going to be 3. So the value is going to be 1 by 3. So the value for your Markov inequality, value of probability using Markov inequality is less than or equal to 1 by 3. Now let us move to your Chebyshev's inequality. So when you have to apply a Chebyshev's inequality, we know that for one-sided Chebyshev, we'll have to apply because it is only greater than or equal to part which has been given to us. So probability of x greater than or equal to your a will be less than or equal to your can I use your sigma square by sigma square plus c square? Will this formula be applicable? We will have to think about that because we have been given mean to be equal to 1. Is mean 0? No, mean is not 0. So will I be able to apply this formula? No, I cannot use this formula. So which is the more suitable formula? I'll have to apply probability of x greater than or equal to mu plus a is less than or equal to sigma square divided by sigma square plus a square. So in this case, mu plus a is going to be equal to your 3. So your mu we already know is going to be 1, is going to be a, which is 3. So my a is 3 minus 1. So a becomes equal to 2. What is the second thing I need for my Chebyshev's inequality? I need sigma square. What does our sigma square represent? Sigma square represents variance of your exponential distribution. What is the variance of exponential distribution? It is 1 divided by lambda square. So this also becomes equal to 1. So my probability of x greater than or equal to 3 will be less than or equal to 1 divided by 1 plus 2 square, that makes it as 4. So that becomes 1 divided by 5. So by Markov, the value is 1 by 3. By Chebyshev, the value is less than or equal to 1 by 5. And we will go for the last case for your actuals. So using your actuals, how to estimate the probability of x greater than or equal to 3. We know that by memoryless property, I can apply, because exponential distribution has a special nature of satisfying the memoryless property, which says x greater than or equal to k is e power minus lambda times k. So by which my probability of x greater than or equal to 3 will be equal to e power minus lambda. I know that it is given as 1 to me, 1 times of 3. So this becomes e power minus 3. So when you have this to be worked out in your calculator, we see that 1 divided by 3 will be equal to your 0.333. Your 1 divided by 5 will give me the value as, say, 0.2. And what is going to be e power minus 3? So this will give me a shift and e power minus 3, which is going to be 0.0497. So by x greater than or equal to 3, this has to be less, sorry, not less than, this is actual, equal to 0.0497. This is my actual answer, and we say that 0.2 is more closer to the actual answer than the 0.3 which we get through Markov. So this says that Chebyshev is able to provide a better bound for moving towards your actual answer rather than Markov inequality. So this gives a comparative way of doing problems using various inequalities and how we can compare them using your actuals. Hope you enjoyed this session. Happy learning. Keep learning.